Page 367, lesson 7.3 is on understanding experimental probability. So the last section we talked about theoretical probability, kind of like what we would expect to happen. Experimental probability, if you look at the word, the first part of it is experiment. So this is like if you actually do an experiment, it's what actually happens, basically, is a way of looking at that. So if you look on this, solve and discuss it, it says Kevin is awarded a penalty shot. He will either score a goal or not score a goal. Are both outcomes equally likely? So it's kind of like there's two things that could happen, either scoring a goal or not scoring a goal. So the question is there the same chance of him scoring a goal or not scoring a goal, or is it going to be different than that? So there's actually a lot of variables for this, and we could say just because there are two options doesn't mean they are equally likely. So it kind of depends on, how good of a player he is, how good of a player the goalie is, different things on. It's a penalty shot, so there's no other players involved. It's just him and the goalie. So there's, we don't have to worry about if they have a power play or all these other different possible hockey options that we could have. But again, it's not just flipping a coin, heads or tails. It's not like flip a coin and see if he's going to score or not. So on example 1, Talia and Yoshi plan for 1 out of 8 or 12.5% of the players winning a prize. During the school fair, they kept track of the numbers of total players and winners and recorded the data in the table below. How does the actual number of winners compare to the expected number of winners? So if you look at this overall, they kind of broke it down by time frames, but overall there were 475 people that played the game and 58 of them won. So from that, we can figure out what the experimental probability is. Experimental probability, the book gives a definition over here, kind of. They mentioned on the left side of the page relative frequency, which we'll talk about in a minute. But experimental probability, we could think of it as what actually happened in your experiment. So what actually happened is the experimental probability. So like if I flip a coin, theoretically, 50% of the time I get heads, 50% of the time I get tails. But experimentally, in my experiment, when I flip the coin, it's not necessarily going to exactly be that. Another way of thinking about experimental probability is it's like the number of favorable outcomes over the number of possible outcomes. So favorable outcomes is just, how many times did the thing that we were looking for actually happen compared to how many different possibilities were there altogether. So if you look then back over on the left side of the page, the book talks about relative frequency. Experimental probability is a lot more common of a term, I would say, than relative frequency. So that's why I started with that. Relative frequency is basically, it's the same as the experimental probability. Okay, these are kind of like synonyms to each other. So what they did here is they actually looked at the experimental probability or the relative frequency, whichever one you want to call it. They broke it up into time frames. So they said from 10 to noon, there were 22 out of 213 people that won, which we might want to know what percent that is. If you divide that out, move your decimal 2 spots to the right, that would be about 10.3%. From noon to 2, 36 out of 262 people won, and that's about 13.7%. Really, we're more just interested in figuring out overall how many people won, so I don't know why we need to necessarily break that down, but you can see overall 58 out of 475 people won, and that's about 12.2%. So they were expecting 12.5% of the people to win, and actually there were 12.2% of the people that won. So kind of a summary here, we could say that experimental probability is slightly lower than the theoretical probability, so there were slightly fewer winners than what they expected. Pretty close. They were pretty close to what they expected, but just a little bit lower experimental probability. So if you look at the try it, during the second day of the school fair, Talia and Yoshi recorded 43 winners out of a total of 324 players. How does the actual number of winners compare to the expected number of winners? So theoretical probability, just like it was up above, was 1/8 or 12.5%. Experimental probability, they told us there were 43 winners out of 324. So 43 out of 324. So if you divide that out, 43 divided by 324, it comes out as like 0.132716049. We don't need all these numbers because you see the little squiggly line there. It means that we're going to be rounding this off. We are looking to write this as a percent, so you need to move your decimal 2 spots to the right. And a lot of times we'll just round these to the nearest tenth of a percent. So it's 13 point something. In the tenths place, we've got a 2 there after the decimal right now, but after it's a 7. So we're between 13.2 and 13.3. We are closer to 13.3%. So 13.3% of the people won. We were expecting 12.5% of the people to win. So we can see then the experimental probability is greater than the theoretical probability, which means there were more winners than expected. Example 2, Joaquin also kept track of players and winners for his game during the fair. Based on the results shown in the table, how many winners should he expect if 300 people play his game? Okay, now it says based on the results shown in the table, how many winners should he expect? So we're not actually, we don't even know what they're doing to try to win, so you wouldn't even be able to figure out what the theoretical probability is unless this goes back to a previous problem. Anyway, on this, we are going to just look at the overall picture. This top part, we don't really need to do any of that. We're really just interested in overall. So overall, 71 out of 416 people won. And if you divide that, move your decimal over, that's about 17.1%. I will show you a way we can work using that in a minute, but if you do it a different way, you actually don't even have to find what percent that is. You could use a proportion. You could say 71 out of 416 people won, and we're trying to find how many people out of 300 would win. These numbers don't work real great together. There's no real great patterns. And so what the book did, they just said the variable's being divided by 300. Let's multiply by 300 on both sides. Since there's an equal sign, you could do cross multiplication otherwise, would be another option. They worked that out and they got about 51.2. Obviously, somebody can't be like a 2/10 winner, so we're going to have to just round that off. And so they just went to the nearest whole number and they said that would be 51. So 51 winners out of 300. That's technically the least work that we could have to do. Probably doing a proportion, that's probably the easier route to go. Just to mention though, I talked about over here, that was about 17.1%. So the other way you could do this is you could say we've got about 17.1% of 300 people that won. And then kind of like what we've done before, we could just change that percent to a decimal. And then of usually means multiply. So if you multiply those out, that comes out to 51.3. And then we would still say that that would be 51 winners. The deal is, though, if you do it this way, this answer is not quite as accurate because the 17.1%, that was already rounded. That's not an exact answer. And so you take a not exact answer and then you work it out and then you round again. You've rounded twice versus the proportion, you had an exact number to start with, and so you only had to round your answer at the end. You only had to round once. So technically we get the same answer both ways, but the proportion probably is less work and it's probably a little bit more accurate of an answer. Example 3, Amir and Marvin each flip a coin 50 times and record the result of each flip. The tables show their results. So here's what happened. Like I said earlier, flipping a coin, we would expect half the time to get heads and half the time to get tails, but if you'll notice, that's not exactly what happened here. So based on the theoretical probability, first of all, based on the theoretical probability, what are the expected results of the 50 coin flips? Well, theoretically, that's just in theory. So in theory, half the time we're going to get heads, half the time we're going to get tails. So if we just figure out half would be 25 out of 50. So we would expect 25 heads and 25 tails, theoretically. Part B, it says, why might their results be different from the expected results? And kind of what they're saying here, theoretical can be used to estimate results, but it does not guarantee results. But again, also like the book's saying here, the more times they flip a coin, the more likely it's going to be that their results are going to be closer. So like say you only flip a coin 4 times and you get 3 times heads and 1 time of tails. Well, that's 75% versus 25%. That's, you know, kind of both of those are a little bit far off from the 50% we would have expected. but the more times you flip the coin, the closer you're going to be. Both of these, they're probably around, well, the second one here, this would be 40% and 60%. And the other one's even closer. Those in the other one for Amir's, those are even closer both to the 50% that we would have expected. So again, the more times you flip the coin, the more times you do the experiment, more likely that you'll be close to that theoretical probability. So if you look at the try it, Amir and Marvin continue until they each flip a coin 200 times. How do you expect Amir's results and Marvin's results to compare? How will their results compare with the expected results based on theoretical probability? So we could say something like their results will probably be closer than the results from only 50 coin flips, and their results will probably be close but not exactly match the theoretical probability. Like we were saying earlier, the more times you conduct an experiment, then the more likely you are to match up with the theoretical probabilities, at least be closer to them. So the key concept just kind of recaps things again. Again, experimental probability is number of times an event occurs over the number of times that the event is carried out or experiment is carried out. And again, the more trials we do, the closer those should be to each other. So if you look at the do you know how, Kelly flips a coin 20 times. Results are shown in the table where H represents heads and T represents tails. So first of all, on number 4, we actually don't need the table. It is asking for the theoretical probability. Theoretical probability the coin will land heads up is, so that would be either 1/2 or 50%, depending which format you put that in. Number 5, based on the data, the experimental probability for heads up. Now we're actually looking at this information. So experimental of heads up. So we're looking for, out of all their trials, how many times they got heads. It would have been nice if they just did some tally marks here, but that's okay. We can figure it out. So if we count that up, there are 11 times that they got heads, and they did 20 experiments. So the experimental probability of getting heads would be 11 out of 20. Now, 11 out of 20 compared to 1/2, I might have a hard time comparing those to each other. So a lot of this we've been just keeping as fractions to this point, but it might be good for us to get that as a percent. And if you're allowed to use a calculator with this, you could just divide that out, move your decimal over 2 spots. Otherwise, if not, this isn't too bad at all. We know a percent's a number out of 100, so we could just multiply both of those by 5. That'd be 55 out of 100, which is 55%. So technically, either 11/20 or 55% would be acceptable, but like I said, if you get it to be 55%, that might be easier to compare it to this 50%, and then you can say that, the experimental probability was actually higher than theoretical. Oh, and number 6 then is that question. Experimental probability is greater than the theoretical probability.